What's up guys, it's me, Sir Ernest, and today we're going to discuss example 2.3.2 of Fowles and Cassiday 7th edition. So in this case, we're going to look into the variation of gravity with height. So as you can recall, in example 2.3.1 of this book, we assume that the gravitational field G, or the acceleration due to gravity, is a constant. Okay, so that means if you have a particle, that particle near the surface of the earth will experience a force that is negative, and is equal to negative mg g hat. Okay, considering that the vertical is positive upward, and that is assigned to be y-axis. However, the force of gravity between two particles is actually related to the distance between the two objects that exert those forces. And this is given by Newton's law of gravity, where it states that the force is inversely proportional to the square of the distance between them. More specifically, this is equal to negative g mm over r squared, where g is your gravitational constant. You can look that in your books, the value of that. Capital M is the mass of the earth. So if this is the earth, okay, and let's say you have a particle here, this particle will have mass m. Capital M is the mass of the earth. This is the center of the earth. R here would be the distance between the two. Okay, now let's say we define the radius of the earth to be RE, and then this distance, so the distance of your particle from the surface, let's call that x, so that RE plus x would be equal to your R. Okay, simple, right? Okay, now if we're going to neglect all other forces like air resistance and other factors that might affect your motion, okay, and the equation of motion will now become F will be a function of the height, because RE will be a constant. So this Fx equals negative g times m over RE plus x squared, and this is equal to mx double dot. So you will notice that at the surface, okay, where RE is equal to R, the force will now be equal to negative g mm over RE squared. And by definition, this is equal to negative mg. So therefore, this tells us that g is actually equal to g, small g is equal to capital G times capital M divided by RE squared. So this is one way to estimate the gravitational field of a planet, given the radius of the planet and the mass of the planet. Okay, so using this equation, we can substitute it here. So this becomes f, which is a function of x, is equal now to negative mg times RE squared over RE plus x squared, and again this is equal to mx double dot. Now we can solve this by using the relation where x double dot is actually equal to by chain rule, that's derivative of x dot with respect to time, or derivative of x dot with respect to x times derivative of x with respect to x, is now equal to v. This is v, and then this will be derivative of v with respect to x. So using that relation, we can express this as negative mg re squared over re plus x squared equals mv dv over dx. And then we can solve this by integrating both sides. So in this case, no, not yet. Just have to multiply first. Group together the x's and the v's. Sorry about that. So this becomes dx squared, this dx over re plus x squared times negative mg re squared. On the other side, this is equal to mv dv. Then we integrate. At time equal to 0, the position is x equal to 0, and the initial velocity is v naught. And at a later time t, the position is at x, the speed is at v, or the velocity is at v. Solving this would give us this final results as negative as mg re squared times 1 over re plus x minus 1 over re plus x naught, and this is equal to 1/2 mv squared minus 1/2 mv naught squared. So you will notice that this is just your kinetic energy, therefore this would be your potential energy. Okay, so therefore the potential energy as a function of time, as a function of position, will now be equal to negative mg re squared over re plus x. Okay, that is it. This is now your potential energy function. Okay, so that's your example 2.3.2, wherein here we considered that gravity varies with height. Okay, so that's all for now. Thank you guys for watching, and I will see you guys in the next video. Bye bye.